I gotta be honest with you, you have survived the bulk of the weird stuff in chapter 12. You've never done like the rate laws and the rate orders and those integrated rate laws with the graphs and the mechanisms. All that good stuff is totally new. Now I'm hoping we can sit back and relax a little bit, because maybe a graph like this looks familiar to you. In first year chem, we usually talk about graphs of potential energy, where we've got potential energy in kilojoules versus reaction progress, which is kind of the same as time. As time goes by, the reaction progresses. At the beginning of the reaction, you have your reactants. So here are my reactants. At the end, I have my products. Excellent. Now you might notice here that your products are at a lower energy level, which usually means the reaction is exothermic. Delta H in the middle here is negative 226 kilojoules, meaning it's exothermic. Technically, delta H can be calculated as energy of the products minus energy level of the reactants. Products minus reactants. So if my reactants are at a high level, my products are formed at a lower energy level, somewhere along the line we released energy. In this case, we released 226 kilojoules. Now another part of this graph that I'm hoping is familiar to you is this little bump on the top. Do you remember how like all reactions need a little bit of energy to get started? We call that activation energy. Now it doesn't always seem as if we have to supply heat or we have to supply an electric current, which we'll talk about in a little bit too. Remember that, temperature, for example, only measures average kinetic energy. So let's say I have a reaction that forms a precipitate. It's a reaction in solution. Some of those particles may already have sufficient energy to start the reaction. So you personally don't need to heat the beaker or whatever. But that doesn't mean that there's no energy being added to get the reaction started. We always have to add a little boost of energy to break the reactant molecules and get us to a point where we can rearrange the atoms and form new products. It's just that sometimes the particles themselves may already have that amount of energy. The activation energy is this little bump on the top here. So we can label that as EA, activation energy. And they're listing it here as 134 kilojoules. So I have to add 134 kilojoules to get this reaction started. Now technically, once I get to a point where the reactants have sufficient energy to form products, we actually release about 360 kilojoules of energy. We're going to release 134 kilojoules, plus we're going to release another 226. Well, technically, we don't include that activation energy as part of our overall delta H. It's energy that you have to add to get the reaction started, but then it's produced as we start forming products. We release that same amount of energy, so it kind of negates itself. So really, the overall delta H, the energy change for the chemical reaction, is just the difference between the energy level of the products and the reactants. We don't include that activation energy bump, especially for exothermic reactions such as this one. It's energy we add, but then we get it back. Now, the thing that maybe you haven't done a whole lot of in first year chem is this thing. What the heck is this transition state? Or they'll also call this an activated complex. The activated complex in this transition state, it is just that. It makes sense. It's this temporary arrangement of atoms when you have sufficient energy to start like breaking the bonds and start to make new bonds. sometimes we get this transitional particle. It's not the final products, so it doesn't last long. And you often don't even notice that it's formed. But it is like this temporary arrangement of atoms once I have sufficient energy to get the reaction started. So it's always like at the peak of the energy curve. We'll do a reaction in class where the activated complex is actually a different color. So you can tell when the reactants have sufficient energy to start forming products because there's this different colored solution formed. That's your activated complex. It's a different color than the products. So when we form products, then we know the reaction has gone to completion. But while it changes to this like transitional color, we know that we're at the transition state where this activated complex is present. This temporary arrangement of atoms. We're close to being able to form products. We have sufficient energy. Now the other thing that we should mention about this graph is the reverse. So this is the graph of an exothermic reaction. Exothermic reactions typically have this general shape where your reactants are up high, you add a little energy, and then your products are down low. If I had an endothermic reaction, it would be the reverse. My reactants would be at a higher energy level, my products are at a low level. In order to get from the products to a point where I have sufficient energy to go back and form the reactants, you have to add a lot of energy. To send this thing backwards, I not only need to add the 226 kilojoules that was released, but I also need to add the 134 kilojoules of activation energy. Together, that gives me a total of 360 kilojoules that must be added to reverse this reaction. Oh, okay, that's not so bad. So let's look at an example. Good typical graphs. The exothermic graph, piece of cake, makes sense. You've got your reactants up at a high energy level, your products are at a low energy level. The amount of energy required to achieve this activated complex, that is your activation energy, where the particles have sufficient energy now to collide, break the original bonds in the reactants, and start forming new products. The difference in energy level of the products and the reactants is your overall delta H. Those would be the typical parts of this graph that I'd be able to label or identify. So here's the endothermic graph. The endothermic graph has your reactants down at a pretty low energy level. And again, now in order to get to the activated complex where the particles have sufficient energy for a reaction to occur, you've got to add a lot of energy. This whole thing here, to get me up to this activated complex, that's activation energy. It's a lot. Endothermic reactions are sometimes harder to get started because you have to add a lot of energy. Or sometimes we'll say that exothermic reactions are more likely to be spontaneous. You have to add a little boost of energy to get it started, but it's pretty significant as compared to the amount of energy you get back. Once an exothermic reaction has started, the energy produced kind of sustains the reaction and keeps it going. So we typically say exothermic reactions are more likely to run spontaneously. An endothermic reaction obviously needs a constant source of energy, and it's a significant source of energy in order to get to the point where I finally have enough energy to make products. And anytime you make products, they should be more stable. I mean, otherwise, why would a reaction occur? So we'll say, we'll breathe a little sigh of relief when we finally form the products. So again, the overall delta H is the difference. How much energy did you have to add, which in this case is significant. But when we do finally form the products, we'll release a small amount of energy. The products should be more stable. So the difference, the overall delta H, is the difference just between reactants and products. Now this time, with an endothermic reaction, we should get a positive delta H. I have a net gain in energy. Or if I go products minus reactants, I should have a positive delta H value.